Now, if you've seen any of my other videos, you probably know they're kind of long, a little bit boring, and really stupid. And this video will be no different. I wanted to respond to someone who sent me a post on a issue with their lighting. And basically the issue that they were having is that their headlight was working, but it really wasn't working at its optimal performance. It was just kind of dull, kind of dim, wasn't really projecting the beam out. A lot of times when you're dealing with lighting, you're dealing with a ground issue. That's generally probably going to be 99% of the issues that you're going to have. As long as your power source is up to par and that's working correctly, it's usually going to be on your ground. We talked earlier about the Madass electrical system. You know, all the components are real out there in the open. Your switches are out there in the open, real accessible for moisture, dirt, grit to get into those connectors and create all kinds of electrical issues. Well, you've probably seen this before, and no, it did not fall off my bike. This was purposely removed, just to kind of show you. The main issue that people have with their headlights is really a ground issue, and it happens from the bulb to the actual body of the headlight itself. Because it's so open, you get a lot of moisture, a lot of dirt built up there, and you do not make a good contact between bulb and the body into the ground. The wire we have here is just a power inlet. This comes, so you have like a white wire that touches into this, and then of course your ground leads from this side. A lot of times when you're doing any type of electrical testing, a lot of it's just going to be common sense testing. So if you feel that you may have a bad ground somewhere in this area, you can actually do a drop volt testing between the actual bulb and the body itself to find out if there's an issue or you're having voltage drop between the light bulb and the body itself. A lot of times I'm just so lazy, I'll just hook up a power lead to it or just keep the power lead hooked up to it. I always keep a lot of these little jumper cables around just to do all kinds of fast testing where I don't want to hook up my whole multimeter, and you can just connect this. So I have one to the power, one to the ground, find a viable ground, kick it on, and of course we have light. If I don't have light and I feel it's in the body, then I'll go directly to the bulb itself, and I don't know if you can see that, I can see it right into the bulb, and same thing, I got light. So that will tell me if I have an issue between the body and the bulb ground. If there is a problem there, of course I'll remove the bulb, clean the areas, retest, and we're probably good to go. So again, like I say, a lot of times when you're dealing with any type of electrical issues, a lot of it's just common sense testing, flipping on and on switches, disconnecting connectors, plugging connectors back and forth. But if you really get stuck in some area and you're not getting the optimal performance out of your electrical system, we can use a technique called volt drop testing, and it's a real nice way to find out the dynamics of a working circuit while it's operating. And I'm going to simulate this just, you know, because the other bulb from the Madass is just, you know, it's kind of big, it's kind of cumbersome. This makes it a lot easier for me to kind of show you. So right now we're going to close our circuit, open our circuit. And right now we have our connecting leads to our power source. The green is going to represent the ground side. The black lead is going to represent the positive side. The switch that I have on the ground side right now, really all it is just an interruption of the circuit itself. So right now the circuit is open, but of course if we were to close the circuit, you see the light comes on. So that's all the thing the switch is doing. It's just connecting these two wires together, closing the circuit, our component comes on. Pretty simple. When I do volt drop testing, I try to emphasize that always check your power source first. You need to check the integrity of your battery really before you condemn any components or before you do any type of testing. So the only thing I'm going to basically do is I'm going to just take my black COM lead and I'm going to go directly to the post of my power source. I'm going to take my red lead and go to the post of the power side of the battery. And let's get that off of continuity because that's not too good for a multimeter. And then we'll go directly and we have 12.52 volts. Okay, the battery's going to check good. You know, anywhere between about 12.4 and above, you're probably okay with the battery. What I like to do is I like to get a baseline. Some type of a working baseline of what kind of voltage is the battery using, or what my component is using as the battery is running. or as my circuit is on. So we'll take another test. And right now we've dropped down to about 12.15 volts. Okay, this is going to be okay. When we're running through our circuit here, we want to be within probably a half volt of our allowance. So if we're running, so just for an example, if you're running 12.5 volts on a running circuit, 12 volts is going to be an acceptable range. I'm not going to test it all the way through. I'm just going to try to cut to the chase. I'm going to go directly, as close as I can, to the component I'm trying to run. And what I want to basically do is, I'm just trying to make sure that all my potential for my battery, all my 12.15 volts is getting to my component. So as I keep my COM connected to the negative side of the battery, I have my multimeter set to DC volts. We'll check it again. Now we were running 12.15 volts. Let's see where we go from there. Okay, we're at 11.98 volts. We have a little voltage loss, but you know, again, we're within our half volt parameter. So we're looking pretty good. We have good power going in. Now when we check the ground side, we should show very, very low little voltage, because remember, we want all that potential being used by the component we're trying to run. We don't want to lose anything out the back door. So if I go to the, get my fat hand out of there, if we go to the ground side, now we're running 57.3 millivolts. Now, millivolts is just nothing. So this is a working circuit. This is working fine. There's no issues here. The light is bright. Now if we create some resistance on the ground side, we're just going to add a little friend here. And let's go ahead and close the circuit. And I don't know if you can tell by the video or not, but the bulb has become much duller. It doesn't have that bright, brilliant light any longer. So again, we want to go ahead and check our power source. We're at 12.2 volts, and we want to check our power side just as we did before. We want to make sure that 12.2 volts is getting to the component I'm trying to run. And we're at 12.08. We've had a little bit of a drop, but we're still within our half volt allowance. So again, like I say, our power side is okay. There's no problem on our power side. But if we go directly back to, again, to the ground side, if I can get a good connection here. Okay, now we got 6.0 volts. Now this is not millivolts. This is full 6 volts. So we're about 12 times over our allowance. We have a problem on the ground side. So we need to isolate that issue and find out where is the voltage thief. Where is the breach, not so much the breach of continuity, but where is the disruption. So if we go from the load itself, we're at 6.16 volts. Our problem's still there. And we're just going to go keep tracing back till the end of the battery. 6 volts. 6 volts on the other side of the switch. And we keep tracing it down until it drops down to normal again. So once we get past the voltage thief, now we're at 30.9 millivolts. We passed our area. So now we know that problems between here and here. And all we're going to do is test back and forth until we retain back to our normal fit. We find the issue, correct it. And you can see the bulb is much brighter again. And that's just volt drop testing. We just need to identify. Now, another issue one of the members had was with the tail light. And as I recall, that scenario went is that the tail light worked, but the brake light didn't work. Well, the first thing that comes to mind, you think, okay, I got a bad bulb, and that's a logical conclusion. And it probably was a bad bulb. But nevertheless, if you really wanted to test the bulb to ensure the bulb's integrity, there's a couple different ways you can do this. If you ever look at the Madass bulb, it's almost like a dual-purpose bulb. It actually has 2 small coils inside the bulb. One operates a brake light, the other one operates a tail light. When I read the post, I knew his ground was working good because his tail light was working good, and it's because it shares the same ground, which is just the sleeve of the bulb itself. But on the back of the bulb, you have 2 power inputs, one for the brake light, one for the tail light. So we know there's an issue with the brake light area. And it's easy to test that. You can actually do it a couple different ways. You can check continuity just to make sure that both the coils are complete, they're not interrupted or burned out or broken. Just take your black comm and you want to connect it to the sleeve. And if you can do that, it's not that easy, trust me. And we connect it to the sleeve. And all we're going to basically do is we're going to check each probe. We have good continuity on that probe and on that probe as well. So both the coils inside the bulb are complete. So this bulb should be operational. If you really want to break it down to certain values, and anytime you're dealing with a component, whether it be a light bulb, whether it be an ignition coil, you're dealing with some type of a value that's assigned to it. You know, it's probably somewhere in the Sachs manuals on our forums. There's probably some type of a value chart for a light bulb. I don't know what it is, but nevertheless, I don't really need to know, because if you look close enough on those two coils, one of those coils is thicker than the other. A thicker coil is going to create more resistance. More resistance is going to be more heat is going to create a brighter light. So I can just tell by ohms which coil or which power point is going to be the brake light bulb and what coil is going to be the tail light bulb. Again, we do the same thing. We've got to make sure we're connected to ground. And this time we're just going to test for continuity. Or no, I'm sorry, not continuity, but for ohms. So if I test the first post, okay, we're running probably about, about a half ohm. That's probably going to be the tail light. If we check the other probe, you see we're jumping up and we're about 3 ohms. This is going to be the brake light bulb. The purpose of that, if the bulb is operational, we need to identify where your power point is. That way we can go into the socket, know what point we're going to be testing, and follow that through the switches until we find the breach of continuity. But that's very simple to test a bulb. But yeah, nevertheless, that's kind of how you can do it if you want to spend that type of time. Same member also had an issue with I think what was happening, he had a brand new battery in his bike, and he would, store his bike for maybe 2 or 3 days, and then go try to start his bike up, and his battery would be completely dead. Something was draining the battery when the key was in its off position. This can only happen really on this bike for a couple different reasons. Probably the most common reason was probably his rectifier regulator was failing, allowing extra voltage to escape from the battery and through like a leaking diode. But you can check that. All these like electrical things, there's always some type of a test before you condemn a component. And if you want to do some type of what they call as a parasitic draw, and the parasitic draw is just basically seeing if there's any voltage flowing while your ignition switch is off. Now, most cars or automobiles, you're going to have a little bit of amperage, because you're generally having maybe like a clock running in your car, or you may have some type of module memory running. But on the Madass, you really should have virtually no voltage being lost from the battery when the key is in its off position. So basically all I'm going to do is I'm just going to take my black comm, I'm going to hook it up to the post of the positive side of the battery. I'm going to take the other comm and I'm going to hook it right up to the other connecting portion to the battery. So your connector is disconnected from the battery, but you're connected it through your multimeter, such as I have here. Now I turn it to DC volts, and right now I should have nothing running through this. And I'm at like, you can see it just wandering around right now because there's no voltage dropping out. It's like in some type of millivolts, and like it's just wandering around because it doesn't know what to do. But if I turn the system on, you can instantly see we're at 12.5 volts. So something is staying on his bike when the bike is in its on position. But if you want to identify that you actually do have a parasitic draw when the key is in its off position, probably the first thing to do is just unplug the rectifier regulator. And if your voltage drops down to nothing again, that's your issue. Remove it, replace it, retest.